This is a video lesson for Introduction to Circular Motion Forces. The essential questions for this lesson are, in what direction must the net force, or the unbalanced force, act on an object to make it turn in a circle? And how are tangential velocity and net force related when an object moves in a circle? All right, so let's talk about what causes something to move in a circle. So what force is making the tennis ball travel in this circular path? The force that's acting on the tennis ball as it's moving in the circular path is tension. So the string is attached to the tennis ball and something is holding on to that string and causing it to spin around. So in this case, it's tension that's causing the ball to travel in the circular path. But we call the tension in this case, we call it a centripetal force, because anything that's causing circular motion is called a centripetal force, and that force can be lots of different things. In this case, it's tension on the ball. So now we have the same tennis ball spinning around in a circle, but now it has force vectors attached to it. We can see the red arrow pointing into the middle. That's the centripetal force. And the red arrow pointing perpendicular to the centripetal force is called the tangential velocity. So any object that's moving around in uniform circular motion, like this tennis ball, is going to have a centripetal force pointing into the center, which in this case is tension, and it's going to have a tangential velocity, which is perpendicular to the centripetal force. So what happens if that force disappears? If the centripetal force disappears, what happens to the tennis ball? Where's it going to go? Well, to figure that out, we have to look at the tangential velocity. So if the string were to disappear at this point right here, the tennis ball, so string disappears, centripetal force goes away, and the tennis ball flies off in the direction of the tangential velocity. So whenever the centripetal force goes away, the direction that whatever object is going off in is traveling in the circular path, the tangent it's going to fly off in the direction of the tangential velocity. So let's talk about the factors that change the amount of force that's needed to keep something moving in a circle. So here we have the tennis ball spinning around again, tennis ball on a string, spinning around again. Now we have that same tennis ball spinning around with the force vector. So this is a centripetal force. You can see it's a decent sized centripetal force pointing into the center as the tennis ball swings. And the centripetal force is directly proportional to the square of the velocity of the tennis ball. That's the tangential velocity. So the faster the tennis ball goes, the greater the force. And that's squared. So force squared, so the velocity squared is directly proportional to the amount of force that it takes to swing the ball. So now we have a tennis ball on a much longer string. So how does swinging a ball or swinging an object, rotating an object around the middle, change the force needed if the radius is much longer? Well, here we have the same tennis ball with the same longer string, and you can see from the equation or from the proportionality that the force is inversely proportional to the radius. So the greater the radius, the less force is necessary to keep the ball spinning in a circle. And for another example, the tennis ball with a much shorter radius, the force is much greater to keep it spinning. You can see the vector, the force vector, is very long for the tennis ball with a really short string, because the force necessary to keep the tennis ball swinging is much higher for a shorter radius, because it's 1 over the radius. So the smaller the radius is, the greater the force necessary to keep it spinning. Now, how about if we change the mass of the object that's spinning? So here we've got the same length of rope as the tennis ball was on originally, but now we've changed the mass. We've increased the mass a lot by adding a bowling ball. So how does the force change if we've got a bowling ball, a much greater mass, instead of the light mass of the tennis ball? Here you can see our proportionality with mass is the same as the proportionality for velocity, except that it's not squared. It's a direct relationship. So the greater the mass, the greater the force it takes to swing it, which makes sense. The greater the force to keep it going in a uniform circle. So the greater the mass, the greater the force necessary to keep the object moving in a uniform circular motion. Okay, so we figured out our proportionalities. So now how do we combine all these together to create an equation for the sum of forces for the centripetal force? So we've got a direct relationship with velocity squared. We've got a direct relationship with mass, and we've got an inverse relationship with with radius. So our equation ends up being the sum of centripetal force is equal to mv squared over r. So mass times velocity squared over the radius is equal to our sum of centripetal forces. Okay, so now we have our force for centripetal force. Now we can look at a new type of acceleration. So we have the sum of centripetal forces is, again, mass times velocity squared divided by the radius. If we solve this equation for acceleration, remember that Newton's second law says that F is equal to ma. So here we have just taken F divided by m, which has allowed us to solve for the acceleration, the centripetal acceleration. So, and our F is mv squared over r, which gives us a new acceleration. Our centripetal acceleration is equal to v squared over the radius. All right, so let's talk a little bit about the difference between the two types of acceleration. We've got our tangential acceleration, which is the type of acceleration that we've always talked about before this point. So tangential acceleration changes an object's speed. So that's the type of acceleration that we've dealt with prior to now. So we have our acceleration is equal to change of velocity divided by change in time. So if you think about it graphically, we have an object is speeding up over time, or the object is slowing down over time. So that's tangential velocity. Now let's take a look at centripetal acceleration. That was tangential acceleration. Now we're going to look at centripetal acceleration. So in centripetal acceleration, we have a change of the object's direction, rather a change in the object's velocity. So our equation for centripetal acceleration is centripetal acceleration is equal to v squared, so the velocity isn't changing, divided by the radius of the circle. So here we have a car that's changing its direction. It's going around the circle, but its velocity is constant.